to the constraint, but it doesn't say anything about, so Lagrange will find points that could be mins or maxes, but it doesn't say anything about the derivatives there. Just like in one variable, you don't really care about the derivative at an endpoint. Right? It could be big, it could be small, you don't know. All that you care about is that endpoint could be a max. Right? In this picture, this endpoint is a max. Here, in this picture, all our endpoints are mins.
But then the constraint has an infinite number of endpoints, right? So what is special about the ones that Lagrange picks?
Those are the ones that could be maxes or mins. So those are the ones that when you plug them in here will give you maxes or mins. Yeah. Maybe we should do a little computer visualization of what this looks like. Is that all right if we graph this? Just have to turn on the projector and it takes a long time. Okay, so what do we got? In our question, we've got a circle as our constraint, and then our level curves. Look something like this. So I want to give you the 2D picture and the 3D picture of this graph. Okay, so there's the function that we're optimizing. Notice that it's a sort of a paraboloid, like it's sort of a parabola but squished a little bit. Oh, I made it so okay. Okay, sweet. Okay, so in the 2D picture, it's easier to get a sense for what's going on because we're two-dimensional creatures. We mostly see things in 2D. So the red curve represents our constraint, right? That's the set of points that we're trying to maximize over. The blue curve represents the level sets of our function. So I'm going to change the height of the level set, and that will change the shape of the blue curve. Okay. So what this is saying right now is that for values like -0.3, the level set never touches the constraint. Right? So everywhere on the red curve, our function is bigger than -0.3. Now we'll increase a little bit. Right? The blue curve gets bigger, but still at -0.1 they never touch. Now they touch. Okay, so at 0, the two things are tangent, and Lagrange is the tool that picks up that tangency. Lagrange is the thing that says, at that point in time, you have a point of tangency. Okay. what does that correspond to in the 3D picture? In the 3D picture, it's corresponding to these guys touching right here. So it's corresponding to the fact that those two curves touch on the boundary of the cylinder. So the boundary of the cylinder, there's sort of a dip. See right there. That represents one of the tangencies. Right? If we sort of look at it from above, we can see that picture. Okay, now we increase t some more. It gets bigger and bigger and bigger. And there's a second point of tangency. Okay? Right, so we go up along the paraboloid even more. Boop. We get a second point of tangency. Now, we've gone up in height. We've moved upwards in height as that blue curve has gotten bigger. So that corresponds to the point of tangency that is very high up on our graph, which should be up here. Okay? So I should make these colors match. That'd be kind of neat. Oops. Okay, so the blue cylinder represents the blue paraboloid represents the changing objective function. So when the objective function is very big, it has a point of tangency way up here. That's our max. And when the objective function is very small, it has another point of tangency, which is this guy here, this lower point. Okay? And Lagrange, this equation is picking up the moment when those two things touch, when they have parallel gradients. Okay. Are there questions about this 3D picture or the 2D picture at all? Yes.
What if we had a function which overlapped completely on top of the circle that our constraint is right now?
Overlapped completely.
So if it was like a cone, which we're going up levels and the circle increases, right? What if at some point the entire thing overlapped? So what would Lagrange multiplier?
So then there'd be tangent everywhere, right?
Right.
Right. Okay. Yes, I see your question. Yes. So if you had like a cone, okay. You're actually let's just draw the situation you're talking about. Right. So here they sort of something like this where they're the whole circle is occupied by this same thing, right? There's sort of tangent everywhere. So what you would get is that in such a case, all of the points would be maximum and all of the points would be minimum, right? So here, if I'm looking at this, it only goes up to height, I guess 1. So every output of my function is height 1. So 1 is the max, and also paradoxically 1 is the min. Right, because it's constant, right? So its min is equal to its max. The usual situation though is where you have distinct maxes and mins. Does that help? Does that answer the thing?
Yeah.
More things people would like to know about this setup. So I think that by sort of playing around with Desmos and GeoGebra, you'll learn a lot more than I can explain to you. So like, where's the slider? So by playing around with this, you'd be able to move this tangent plane. So if you, or this horizontal plane, and that horizontal plane is showing you the cross sections of what's going on. So if you look at it from above, right, you see the red circle and then an ellipse, right? So that red circle is our constraint. The blue ellipse is what we get when t is 1. When we cut at height 1, we get a picture that looks like this, right? Which is what we're seeing here. Ellipse, or here, maybe I should. Right, there's the slice at t equals 1. If we go to t equals 2, we get a slightly different picture. Right, and if we raise that cross section a little bit more, right, we'll get slightly different pictures as we raise and lower that cross section. Right, so if we go to height 4, oh, now it no longer touches our graphs. Oops. We get a picture that looks like this. Okay, so I encourage you to play around with these things. Okay.
I had another question.
Sure, perfect.
So, will we always only have one constraint, or can we have multiple constraints? For example, here we have 2 circles, x squared plus y squared is 1, x squared plus y squared is 2, and everything in between.
Right. So yes, that's mathematically possible. In this course, we'll just do one constraint.
Okay.
It's hard enough. It's confusing enough. But yeah, so if you look at the textbook, the section on Lagrange does have material about multiple constraints. We'll just be doing one constraint on quizzes and term tests and stuff.
Right.
Are there any other questions, thoughts there? Okay, so I wanted to solve that last question on the thing. So the major idea for today is if you have a less than or equal to, then you split it into an interior and a boundary, and analyze both of those separately. Over the reading week or the break, I encourage you to check out the mock term test. Very good study guide to our test that's coming up. If you wrote the mock term test, I have your paper and I've graded the multiple choice and the and I've put comments, you know, sort of how you did, suggestions on how to review. So if you'd like to come and grab that, you're welcome to. And if you didn't write it, there's some candy for you. So please come up, grab some candy. And if you've got any questions about organizational things, please come up and ask. And then I guess we're done. Thank you, John. Yeah, like different magnitudes, and that could give you,
Yeah, just the other stuff.
or like that, like would be bigger, like that. So
he
let's,
circled this, the converse to this makes it be on a level. And then he said hit this, so you just circled it, you did that one.
How did you do on the?
We did that one. Cause I mean, we did all of them, right? And then we did all the points. No, he's like, he picked it before he did twice. Cause if you look at it, right, we got, first we got this one, 0, it's also here. -1, 0, so technically, like, yeah, it's on.
I actually
But like, I remember like, I took
What do you want? What's golden? I wonder why. The ball.
yeah,
Or, you know, you just like to just take all the water and
like, so you do like, yeah, like,
Was it someone they jumped up to or something? Beforehand. Okay. I got like a really sensitive camera.
Oh yeah, I know. I just like SMS. Oh, so you can stay, yeah, I'm gonna.